we go. Today we are simplifying radicals. Radicals are also known as square roots, and that is the square root or radical symbol. And you can say radical, you can say square root, they mean the same thing. The way that we simplify square roots is to know our perfect squares. And so hopefully you know all of these perfect squares, because if you know all your perfect squares, then life is a lot more simple. So what is 2 squared? 4. And what is 3 squared? 9, because 3 times 3 is 9. And what's 4 squared? 16. And what's 5 squared? 25. And 6 squared? And 7 squared? 49. 8 squared? 64. 9 squared? 10 squared? 100. 11 squared? 121. And 12 squared? 144. Very good. Now, if you didn't know those, you need to have them. No, you need to memorize them. And that's 169. 13, yeah. And technically, you probably should know up to 20 squared. Okay, so 20 squared is 400. But so it is good to know all of them. They will come up. 10 years ago, I used to have my students memorize their squares up to 20 squared. So it's helpful. You will have to learn some perfect cubes and 4th powers and 5th powers as well. So we'll do those as well. I want to talk about perfect squares. So 4 and 9 and 16 and 25 and so on and so forth are called perfect square numbers. And the reason they're called perfect squares is if you go way back to elementary school, where you had the multiplication chart, 1, 2, 3, 4, 5, and so on and so forth, and 1, 2, 3, 4, 5. You remember that multiplication chart? And you would fill in that multiplication chart way back in elementary school. And 1 times 1 was 1, and 2 times 2 was 4, and 3 times 3 was 9, and 4 times 4 was 16. And you had this whole chart to fill in. Well, it turns out all of the perfect square numbers always fall on the diagonal, right? Kind of interesting. But the reason they fall on the diagonal is a little less noticeable. They fall, and 2 by 2 creates a perfect square. And 3 by 3, again, creates a perfect square of 9 units. So when you look at that multiplication chart, it literally is 9 units, and they form a perfect square, or 16. Oh, that's good. 16 units, and it arranges itself in this beautiful perfect square where 16 falls in the last spot. Okay, so the reason they're called perfect squares is a literal thing. And that's kind of interesting, right? It's called a perfect square because it literally forms a perfect square. Okay, and this is the kind of math that I love finding out, because it's like, oh, they actually had a reason for calling these perfect squares, because it actually makes a perfect square arrangement. Okay, and that's really important that we understand. So we want to make sure that you know all of your perfect squares, because if we want to simplify a square root, then knowing perfect squares is really, really useful. So we're going to look for those perfect squares. A square root undoes the perfect square. So if I know that 2 squared equals 4, the square root undoes it. It's the inverse of a power of 2. It's the inverse of that exponent of 2. The square root of 4 takes us back down to its root, which is 2. Okay? So that's the perfect square. That is its root of 2. Okay? So we're finding roots. here we go. Example 1. Simplify the expression. Simplify the expression. There's lots of ways that I teach simplifying radicals, and I hope that you learned how to do this in Algebra 1, but I never really know what people learn or don't learn in Algebra 1. I just can't depend on it. So I hope you learned how to simplify a square root. I'm going to teach it again, but I'm teaching it differently than I would if I were teaching Algebra 1, okay? So to simplify a square root, we have, this is one of our product properties of radicals. I have this square root of the number a times b, all right, under the radical. And what we can do is we have one giant radical. We can break it apart into the square root of something times the square root of something else. So we can break it apart into 2 smaller radicals and then try to simplify from there. What we want to do is break apart our number. We want to look for our perfect squares. We want to look for our perfect square factors. So if I'm going to simplify the square root of 500, I want to break apart 500 into some factors. Well, there's lots and lots and lots of factors of 500, right? But what's a really, really obvious one? Okay, so 50 times 10, that's an option. 50 times 10, what's another option? 5 times 100, huh? There's like, what, 25 times 20? That's another one, I think. Is that right? 25 times 20, is that right? I think so. So what we want to look for are perfect squares. 50 times 10, does that have any perfect squares? No. What about 25 times 20? We got a perfect square in there? Yeah, we do. We got 25. What about 5 times 100? We got a perfect square in there? Sure we do. We got 100. We want to go with the largest perfect square we can find, okay? So we're looking for the largest perfect square. So I can rewrite radical 500. I can break it apart into the square root of 100 times the square root of 5. Lots of choices, but we want to be strategic with our choices. We're choosing the largest perfect square factors that we can find. And then, well, what is the square root of 100? 10. Why is the square root of 110? 10
times 10.
Yeah, because 10 squared equals 100. The square root is the reverse. If you know 100, the root is the 10. The square root and the square cancel each other out. All right, so we're left with the square root of 100 is 10, and then times radical 5. You can write it just 10 radical 5, or 10 times the square root of 5. You should know that anytime we got those two numbers next to each other, the operation is always multiply. All right, you don't see a plus or minus. The operation is multiplication. So 10 radical 5 is how we simplify it. And this is an exact answer. Your calculators can give you approximations of answers. So it's important, especially on my tests, since they're multiple guess. You can check all of your answers, all right? So I want you to practice with your calculators. The square root of 500, my calculator can give me a decimal approximation. It's about 22.3607, roughly, okay? That's the decimal approximation. I can also check what my simplified answer is. 10 times radical 5. And 10 times radical 5 gives me the same decimal approximation. This is 99% of math, 22.3607. So it's super easy to check your answers. And especially on one of my multiple choice tests, if you aren't sure how to do it, then use your calculator, all right? And look at the approximations. Now, these are exact, this is an exact answer, 10 radical 5. This is a decimal approximation. You will rarely give me a decimal approximation, okay? Unless I tell you round your answer to the nearest thousandth, you're gonna leave your answer like this. 10 radical 5 is perfectly wonderful, it's exact, and it's easy. And that's usually how we want our answers. In mathematics, we like things exact. We're not science people. Science is why Mars rovers crash into Mars. Okay, I digress. Here we go. Let's simplify the square root of 24. 24, what are some factors of 24? 12 times 2. What else? 4 times 6, 8 times 3. Which one do we want to use? 4 times 6. We want to use 4 times 6 because 4 is a perfect square. So the square root of 4 times the square root of 6 is how we can break that apart. And then what is the square root of 4? Just 2. The root is 2. So we get 2 radical 6 for our answer. And again, that means 2 times radical 6. All right, square root of 18. What are some factors of 18? 9 times 2, 6 times 3, 18 times 1. What are we going to use? 9 times 2. Again, 9 is a perfect square. So we're going to break that apart as the square root of 9 times the square root of 2. What is the square root of 9? 3. So we get 3 radical 2 for an answer. Do you guys have any questions so far? It's pretty easy, right? All right, here we are multiplying 2 radical numbers together. They're totally radical. So what we can do is sort of this property in reverse. I want to multiply them together under a giant radical. So I am going to say radical 6 times radical 15. What is 6 times 15? 90. So is it 90? Yeah. So I'm going to write it under one giant radical. Then, now I'm back to what we were doing over here. So I want to think about my factors of 90. What are some factors of 90? 9 times 10, 6 times 15, 45 times 2. And again, we want to use 9 times 10 because it has a perfect square in there. Okay? So square root of 9 times the square root of 10. And what is the square root of 9? 3. And I can't do anything with the square root of 10. There's no perfect squares in there. So everything is just hunting for perfect squares. Letter E here, we have 3 times. There's no sign, it's a multiply. Okay, 3 times radical 12 times radical 6. Because these are totally radical numbers, we can put them together. So I'm going to leave my 3 hanging out in front. And what is radical 12 times radical 6? What is 12 times 6? 72, yes. So that's a giant radical 72. Now this 3 is just hanging out in front. He's totally fine. We want to try and find these factors of 72 to break it down. 72 divides by 2 really nicely. 2 times what?
31.
Nope. 36. 36, yep. It's also 9 times 8 and 12 times 6. But again, 9 is a perfect square and 36 is a perfect square. How come I'm going to use 36 times 2? Because it's the biggest. Yes, the biggest perfect square. I have a 3 chilling out in front. And radical 72 is going to break apart into radical 36 times radical 2. Again, 3 is just hanging out. What is the square root of 36? 6. Good. And I can't do radical 2. It doesn't have a root. What do you suppose I can do with the 3 times 6? Multiply. Yeah, they're regular numbers, so I can multiply those together. 3 times 6, God bless you, is 18. And a radical 2 tacked on the end. 18 times radical 2 for a final answer. Okay. Do you guys have any questions on this so far? Okay. Last thing. Example 2. Simplify the expression. Now we're not multiplying. What are we doing? Division. Okay, so here we have a giant radical. Inside that radical, we have a little fraction, a division problem. So again, anytime I have a giant radical, I can break it apart into 2 little guys. All right, so that's what I'm going to do. Here we have the square root of 16/25. One giant radical can be broken apart into 2 little ones. So I'm going to rewrite that as the square root of 16 over the square root of 25. Well, that's nice. What is the square root of 16? 4. And what is the square root of 25? 5. No more radicals on those. Letter B, we got the square root of 12/49. Again, it's one giant radical, so I'm going to break it up into 2 little guys. So radical 12 over radical 49. Which one's easy? Radical 49, right? What is the square root of 49? 7. All right, so that one was easy. That's just 7. But radical 12, 12 is not a perfect square. We've got to break that one apart. So how do we break up radical 12? Any perfect squares in there? 4, yeah. So 12 is the square root of 4 times the square root of 3. And now I know, what is the square root of 4? 2. Radical 3 is going to stay up top, and we're dividing by 7. So 2 radical 3 over 7. All right. Letter C, square root of 25 over 3. Again, giant square root. I'm going to break it up into 2 little guys. So that's going to be the square root of 25 over the square root of 3. Which one's easy? The 25, the radical 25. What is the square root of 25? 5. So right now I have 5 over the square root of 3. 3 is not a perfect square, so I can't simplify it. This is a problem, though. You are not allowed no radicals in denominator. No radicals in the denominator. Your book does not allow you to leave a radical in the denominator. So we have to do what's called rationalizing. Let me talk about why for a second. So we do not teach how to calculate the square root of a number. But I'll tell you the process for doing it is very, very similar to long division. Remember long division? That long, annoying process, okay? The process for getting a decimal approximation for a square root is very, very similar, okay? So long division is hard enough. If we were trying to divide by a radical number, then that makes the division even harder, right? Okay, so you can imagine that just finding the square root of 3 is hard enough. And then to divide it into 6 makes it or 5 is even harder still, okay? So many, many moons ago, like the time of my great-grandmother, they taught how to find the square root of a number. We don't teach it anymore because, thank God, we have calculators, all right? But many years ago, they said, hey, we can't have radicals in the denominator because that just makes the process of finding the approximation too hard, all right, too difficult. So what we're going to do is we're going to rationalize. Rationalize. R-A-T-I-O-N-A-L-I-Z-E. Rationalizing turns out to be pretty easy. We need to do something to get rid of this radical. And what we're going to do is we're going to multiply top and bottom by whatever that radical happens to be. So we're going to multiply top and bottom by radical 3. Why am I allowed to multiply by radical 3 over radical 3? What is radical 3 over radical 3? 1. Yeah. Radical 3 goes into itself 1 time. So in effect, what we're doing is we're simply multiplying by 1. That's allowed because it's not going to change anything. It's not going to change the value of our equation, the value of our expression here. So now I can go ahead and multiply straight across. 5 times radical 3 is 5 radical 3. What is radical 3 times radical 3? Radical 9 under a giant radical. And then what is the square root of 9? 3. Yeah, it cleans up really nice. So I like to say that it resolves. It cleans itself up. Comes to a resolution. Okay? And we don't have a radical in the denominator anymore. Okay? I have a radical 3 on top and a 3 on the bottom. That's a lot of 3's, and it's a fraction. Do you suppose I can reduce the 3's? You cannot, because one is a totally radical number and one is a regular Joe. They don't mix, okay? So here again, last one. We have a giant radical. I'm going to split it up into little guys. So radical 2 over radical 11. Are either of these numbers that we can simplify? They don't have any perfect squares in them. I can't leave my answer like this because we got a radical. So how do we get rid of that radical? What's the word? Rationalize. Use the words. All right, rationalize. So what am I going to multiply top and bottom by? Radical 11. We're going to multiply top and bottom by radical 11. Now, both of these are totally radical numbers, so we can multiply them together. So we get radical 22. 2 times 11 is 22. And the denominator, both of these are radical numbers. Radical 11 times radical 11 is radical 121. Does anything clean up? Yes. What is radical 121? 11. The square root of 121, the root is 11. So we have radical 22 over 11. Can I reduce the 11 and the 22? No, you cannot. Again, this is a radical number. It's under a radical. Totally radical guy. 11 is not. They don't mix. Do you guys have questions for me? It's really important that you know how to simplify radicals and do it well. These are all odd. You can check all of them in the back of the book, but you must show your work. Okay, make sure you show the work. And I highly recommend, I'm posting it to the class website as we speak. I highly recommend doing the evens as well. Okay, at home if you want for extra practice. Okay. This will go pretty fast. You have more than enough time to get it done before you leave, ladies and gentlemen.